All right. We're very happy today. This is actually a special event. It's not only the last seminar of the year in this series, but we have Jack Brouwer here, who is the Associate Director of the National Fuel Cell Center at Irvine. And he's also a co-conspirator of mine in that he and I are both connected with Janet Napolitano's very ambitious goal to get all 10 campuses of the UC system off fossil fuels to reach zero greenhouse gas emissions by 2025. And Jack's been contributing to that activity. That's not the main topic of his seminar today, but he is going to give us a really nice overview of some of the work at both his own work and also some of the work of the National Fuel Center itself. Jack?
Thank you very much. I very much appreciate the invitation to be here today and to talk to you a little bit about some of the research we are doing on next generation power systems. And I have an outline here of the talk that should take you through as I go along. I'll go pretty quickly through the slides, as I must, since I have 61 slides. Supposed to finish that in about 40 minutes, right, Savannah? Yeah, about 40 minutes or so. But what you will see is that there will be a consistent theme associated with the dynamics of energy and power systems. And that's really what I want you guys to leave with, is some understanding that the dynamics are very important. Okay? So the National Fuel Cell Research Center is known for a number of things, but I think in particular I have a picture representing some of the things we are known for with regard to research activities. In particular, the tri-generation of hydrogen, heat, and power, the use of vehicles and hydrogen stations throughout the state, which we've been very involved with, the integrated use of fuel cells and gas turbines, okay, these kinds of next-generation power plants that use gas turbine technology and fuel cells, and then the use of renewable fuel cell systems. And I'll talk a little bit about almost every one of these in the talk today. We also were one of the first universities in the country to establish a fuel cell course, okay, that we have regularly offered since 2000 at UC Irvine. And we participate in lots of other education and outreach activities. To do all these things that I'm going to be talking about today, we have quite a big group of students and faculty who participate in this research. And this is an example of one of our work days. And when we say work, we mean physical labor. We mean scrubbing windows and painting and cleaning up the lab. So you can see here, and we have students from all over the country, all around the world, and really outstanding students. We are fortunate to actually work in an area that's pretty exciting for students to participate in. And as a result, we get outstanding applicants from all around the world. So, energy systems are critical. I know I don't have to say that to you guys because you guys are here as part of the Institute for Energy Efficiency or have other energy-related research interests. But it's critical to almost every aspect of our society. All economies and all sectors of all economies depend upon efficient, clean energy conversion. Even our quality of life, our health care, all of these advances in society have some dependence upon the delivery of power and energy. Even our freedom of mobility, the ability to fly, the ability to drive, to get anywhere, is associated with energy conversion. So these are great things in our society, in economies that are dependent upon energy conversion. And energy conversion is a really great field to study because there's so many different aspects of it. Okay, so you see here some of the things, the important aspects of energy systems. You have things like thermodynamics, fluid dynamics, chemistry, electrochemistry, material science, controls, everything that you can think of really is often involved in an energy conversion system, all these fundamental sciences. But I'm an energy systems guy, and I need to study the complexities associated with putting all these energy systems together. And in that case, I almost always need to make simplifying assumptions. I seriously cannot analyze every aspect of the electrochemistry of a fuel cell, but I need to know something about it. And I need to incorporate that in my analysis of this. And I want to make a suggestion to you today that to do this properly, even at the systems level, I must have some degree of spatial and temporal resolution. And I'm going to show you a few examples today of why I think this is important. I'm going to start with a simple spatial model of a fuel cell that we use in the development of a next-generation power plant. This is an example of the thermodynamic analysis that one would have to go through to actually design an integrated gasifier fuel cell system, IGFC, Integrated Gasification Fuel Cell Plant. I think these are going to be the most important types of power plants for converting biomass and coal in the future. If we're going to do it, this is the way we should do it. These systems are complicated, as you can see here, and this is a simple rendering of this kind of a plant. But they include mainly things like the preparation of the fuel, some sort of a gasifier, all different types are possible, a syngas cleanup step to remove the contaminants and things like that, a solid oxide fuel cell, a gas turbine, a steam turbine, and some CO2 separation equipment for recycle, but also for CO2 sequestration. So this is a type of plant that can actually produce electric power, produce even hydrogen, and do so by separating and sequestering CO2. And it can do so very efficiently. Our analysis of this suggests that we can make a plant that's more than 60% efficient while preparing the carbon dioxide for separation and sequestration. That's almost double the efficiency you're going to get from a typical coal-fired power plant that's doing sequestration. It's remarkable. But all of that analysis, even our own analysis of this up to this point, was for a bulk model of the major system components. So in other words, we study the thermodynamics and the overall efficiency and heat transfer associated with each component, but each component has only one temperature, one pressure, one set of species concentrations, etc. A bulk model. In a fuel cell, we convert the fuel and the oxidant along the length of the path of fuel flow, oxidant flow. So as we're going along the length, we have different species concentrations. We have different temperature. We have heat transfer with the other components in the system that all have an impact on how that fuel cell will perform. And so far, we haven't resolved that. So I want to suggest that I want to make a really simple model, but I want to resolve some of the spatial and temporal distributions of species concentrations, temperature, etc. So I'm picking just one channel of a middle fuel cell, and I'm resolving the length of the flow channel. So we have fuel flowing on one side, air flowing on the other side, and I'm making electricity from this fuel cell. And I solve the species conservation equations. This is the mass and charge balances associated with that, by making some simplifying assumptions. I do only hydrogen electrochemical oxidation. I do some methane reforming and water gas shift chemistry inside of perfectly stirred reactors that are comprised of each individual node of this resolved fuel cell. Now to do the heat transfer, it's a little more complex because I have all of the constituents interacting with each other, and so I use a tridiagonal matrix algorithm to actually solve for all of these temperatures in one simple matrix inversion. Okay? So this is a simplified model of the fuel cell, but at least I resolve then the length of the fuel channel, the length of the air channel as I'm going along, changing temperature, changing species concentrations, having heat transfer with all the other components. So what I'm doing is I'm taking that original model that I had that had kind of a fuzzy, not well understood bulk model. It's operating at 0.8 volts and 73% fuel utilization. And I want to put a more resolved, clear, one-dimensional fuel cell model in its place. Okay, so I stuffed that back in. So what happens to the overall analysis of the system now? what I'm going to show you is the analysis only for the counterflow case, where air is flowing this direction, fuel is flowing the other direction. Okay? We also did it for co-flow, but you can do it for all kinds of different configurations. And I'm including some internal reforming. Remember I told you I had the methane chemistry along with the hydrogen electrochemistry occurring inside of that fuel cell. And what I found, okay, is that the implicit assumption of the thermodynamic analysis without any spatial resolution gave me fuel and air out of the fuel cell at 200 degrees C above the inlet temperature. Thermodynamics works out fine. I want a 200 degrees C temperature rise in the fluid that's going through my fuel cell. That works really well in the system analysis. But if I introduce my one-dimensional model and have the same constraint for the fuel cell, it can only withstand a 200 degree C temperature difference, which actually is pretty stressful on the cell already. That leads to this kind of a temperature distribution. Okay, so this is the temperature distribution of my fuel cell. It's not this implicit one-dimensional increase in temperature. So what ends up happening is my fuel comes in at 650 and only leaves 40 degrees hotter. And my air flow had to be increased 4 times and only leaves 70 degrees hotter to maintain that temperature constraint on the fuel cell. And this is what happens to the analyses. Okay, so this is just looking at all of the major performance characteristics, like how much energy is coming from my steam turbine, from the expander topping cycle, how much is coming from the fuel cell, electrical power, etc. Okay, and what you see is that, hey, I got more air going through my system, so I get a little more cathode expander power, I get a little more total gross power that's made. But I have a huge increase in my SOFC blower compressor. So to push all that air through my system, overall efficiency drops from 61% to 45%. That's horrible. I can't have that kind of a difference between resolving and not resolving the spatial distribution of temperature and species in this kind of a system. Now, there are ways in which you can mitigate this, but you wouldn't even know that you had to mitigate this if you didn't resolve that spatial distribution of temperature, species concentrations, etc. And the idea we came up with to try to resolve this is to cascade the stacks in airflow series and fuel flow parallel. Okay, so you can see here, fuel's coming in at 650 in each one of these cases, and it's leaving at 670 here, all the way up to 719 here. Air is flowing in series here with air addition between each of the stacks. Okay? And in that particular design, I end up having temperature distributions in each of these 4 stacks, stack 1 through stack 4, stack 1 through stack 4. That looks reasonable. That's able to be withstand the thermal stresses of these and produce the power that I need. It doesn't quite get us back up to a 61% overall efficiency, but it gets us to 58 or so, which is still a really impressive number. Okay? Very nice. So all of that analysis is done under steady state conditions. But again, I showed the importance of resolving that spatial distribution of temperature and species concentration. Now I'm going to talk about control systems development, because I think that not only do we need power plants with high efficiency and 0 CO2 emissions, but we need power plants that can be dispatched rapidly, especially to complement wind and solar power. And we developed this strategy using MATLAB Simulink especially as our environment. It's well suited for developing control systems and the like. Okay? We make, again, simplifying assumptions like simplified geometry, okay, quasi-steady state chemistry and electrochemistry, and we resolve some of the major features that lead to the overall performance, like the electrochemical losses, the species and energy conservation equations, etc. And we write them in these dynamic expressions. Okay, so these dynamic expressions for species conservation, momentum conservation, the Nernst equation, the primary equation that governs electrochemical thermodynamics, and then electrochemical dynamic losses that we estimate through these terms that you see here. And then the overall mass conservation equations, again, these dynamic expressions which allow us to solve the equations, okay, for overall performance of a fuel cell, even under dynamic operating conditions, because we're doing it in a simplified geometry like this. Okay, so this is a particular case where I have that planar solid oxide fuel cell, again, only in 10 separate nodes. Not a lot of spatial resolution, but enough. I have another kind of cell here, which is a tubular cell. You can't see that very well here, but these kinds of simple geometries, but incorporating all the physics that I can. And here's an example of the heat transfer network that you have to account for, which includes the conduction, convection, and radiation heat transfer. And we've verified the performance of these systems in many different levels. Here's an example of a single cell where we instantaneously increase the demand from the cell. And you can see the voltage drop, and you can see our models following that fairly well. This is a ramp up in power, going from 19 to 21 kilowatts or so, and you can see our model follows it very well. This is the dynamics of fuel cell voltage diurnally that we actually were able to model very well from a solid oxide fuel cell gas turbine system. Okay, so it's a very complicated system. I got to account for all of the features of it. I must not resolve the fuel cell in all of its geometric features. And then we can come up with strategies for starting these fuel cell systems up, controlling them, dispatching them under high dynamic operating conditions. So in this particular case, this is an example of a solid oxide fuel cell gas turbine hybrid system that has several things that I can manipulate. I can manipulate a recirculation blower. That's this guy right here. The fuel flow, the air preheat, the solid oxide fuel cell air bypass valve. Okay? All of these I can manipulate so that I can control things like the power output. That's what I want to go up and down really fast. Okay? I can control the peak SOFC temperature or the temperature gradient or even this oxidizer temperature that's here. And in this particular case, I'm perturbing the system by suddenly decreasing from 100% to 50% power, instantly dropping the power by half. Now, most of the fuel cell companies I work with say you're crazy to try to do something like that. But the fuel cell itself should be able to rapidly respond to it. The problem that we have with most fuel cell systems is not that the fuel cell inherently is limited. It's rather that the system, in order to protect the safety of the fuel cell and its overall operating characteristics, is slow to respond. Or, if you do it, it stresses the system so much it breaks. But we were able to show, and this is showing a 2D model of the temperature distribution in that cell. And you can see that it doesn't have a big gradient in temperature. And we were able to show that when I subject it to that dynamic, okay, I can keep the peak SOFC temperature less than 1073 and keep the peak temperature gradient less than 150 K during the entire transient. Okay? And usually this shows the transient, but the movie isn't working today. I've also shown this in standalone solid oxide fuel cell gas turbine systems where I'm manipulating fewer variables, okay, but controlling similar things like the system power and the temperature distribution. In this particular case, I'm ramping it up from 25 to 70 amps. Okay? It's like a 3 times increase in total power coming out of the system. And during that, you can see here, this is the temperature distribution. This is the peak temperature, and this is the minimum temperature. During that whole transient, I was able to keep that temperature distribution very nicely maintained during that transient operation. The reformer temperature dropped considerably, but that's not stressful to the system. And what I did is I manipulated the bypass valve and the blower power in this way, okay, to actually get that type of performance. And this is what you see happen to the temperature distribution, okay? So it started out like this, and after a long time, it eventually got to a steady state value like this, even though I instantly changed the current here. Okay, so you can see this is the current distribution, and this is the temperature distribution for that particular fuel cell. Okay, so there are some systems that we want that not only produce power, but also produce fuels. And this is a system integration idea that we came up with quite a long time ago, working with Air Products and Fuel Cell Energy to actually take a high temperature fuel cell, instead of just making electricity and heat, why don't we use some of that heat to actually make a third product, hydrogen, that could be used in other applications, like transportation applications where we have fuel cell vehicles. And fortunately, we were able to convince the Orange County Sanitation District, which operates a wastewater treatment plant that looks kind of like this, okay? You have waste coming in, you digest it, you produce anaerobic digester gas, and that usually goes to a boiler that produces the hot water for you, or it could go to a high temperature fuel cell. And that's what we did. We placed this high temperature fuel cell in its place, which required some fuel treatment, but then we put in a little more of this digester gas, and we get out of it hydrogen that's essentially for free, because it comes from the heat that we otherwise would have thrown away, and I can produce electricity at higher efficiency when I operate it in tri-generation mode. That happens because I have more fuel in my anode compartment. So per unit of electricity I make, I use less fuel. Okay? I can operate at a higher voltage in the fuel cell under those conditions. So this Orange County Sanitation District allowed us to put their plant here. This is where we actually have the tri-generation plant. It's right next to some of these trickling filters where the ducks enjoy the ponds there with the extra material that's in those ponds. And then we also have a dispenser, which is actually very close to the freeway here, where we actually dispense to fuel cell vehicles. And we've had more than 3,000 renewable hydrogen refills at that station. So we're making hydrogen from this digester gas in this tri-generation mode. And this is a picture of the plant. It has a whole bunch of different features. We have to clean up the gas here. It has a mechanical balance of plant that you see here. That's the actual fuel cell. Here's the inverter and electrical balance of plant, because we have to connect up to AC. Okay, this is the anode exhaust skid, which does some water gas shift chemistry. This is a syngas compressor. This is a pressure swing absorption system, which makes pure hydrogen out of the anode exhaust. We compress it even further and then stick it into these hydrogen storage tubes. Now, not only do we have this complex system that does all three of these things, makes hydrogen for transportation, makes electricity and heat, all from renewable digester gas, but we were able to show that you can dynamically operate this thing. You can develop a system that can produce more hydrogen or less hydrogen, produce more electricity or less electricity. And here's an example of what we were able to show. While the system is operating, we can suddenly shut off the demand for hydrogen, which is what we did when this tank got full here. Okay, suddenly shut off that hydrogen. Now it did have a perturbation, as you can see here, in the anode inlet temperature. Okay, but that perturbation was maintained, and even when we went back to producing more, you see we have a little jump in that, but all of these temperature perturbations that you see here for the cathode and for the anode inlets are acceptable, within acceptable ranges, even though we suddenly turn hydrogen production on and off. Okay? Another way that we can use fuel cells in a renewable system is to use them to complement wind and solar power. In this particular case, we did some research where we're taking all of the electricity from a photovoltaic system, and we are converting it through electrolysis to hydrogen, okay? And then from a fuel cell through inverters to power loads. And we did this to power a residential load demand. So what you see here, and some people in the audience may remember graduate students coming to the house and measuring stuff. This is someone's residence. And someone's residence, actually, you can see they did some long-term cooking on this night, and maybe laundry on this night, because you can see all these spikes in demand, right? And it's not a very nice demand to want to meet, right? You typically only have about a half a kilowatt of power desired, but sometimes you need 8. Highly dynamic loads in the house. But what we did is we said, okay, so let's think about actually providing that power to the house in the lab, because the house didn't want to have an electrolyzer, a solar panel, all the stuff in there. So we simulated the use of that same, okay, this exact photovoltaic system we measured. Okay, so this is measured solar photovoltaic power. We put that power through an electrolyzer in this yellow area. And we powered the home with the rest of the power. At night, we ran that hydrogen through a fuel cell and powered the rest of the home. Okay? And what you can see is that in this particular 1 week of simulation, we didn't use any grid power to do this. The problem here is that I needed almost an 8 kilowatt electrolyzer and a 4.5 kilowatt fuel cell to do this, when on average, I only need 0.75 kilowatts. So this is not a nice investment at the individual residence level, but it shows that you can operate these things in a highly dynamic fashion, okay? So that's what's neat about it. One final thing is that we made enough excess hydrogen to run my fuel cell vehicle for a weekly 18-mile weekday commute. Okay, 18-mile weekday commute. So all of the energy came from the sun. I provided transportable fuel. I provided all the electricity and hydrogen for that fuel cell vehicle. Okay. In the end, I think we needed at more of a large scale, okay, we need to introduce solar, wind power at massive scales in order to make our electricity grid sustainable. When we do that and have high penetration of renewables, the key challenge, I think, is to handle the dynamics of renewable intermittency. So this is one of the reasons why I have been harping on dynamic performance as being really important. Because we've studied some of these circuits in real electric utility grid networks. This one happens to be in PG&E service territory, and this is the substation, and then it has all these transformers that you see in green, and all these starred locations where there are significant solar installations. And in this particular case, 1.9 megawatts almost of solar power is installed for a circuit that has a 12 megawatt maximum power delivery. Okay, so it's like 16% of the power on average is met by this, all by the photovoltaic systems that are on this grid. And what we see is that the typical installation of the electric grid is not able to handle all of the dynamics when we have high solar power use. There has to be some change to the controls. There has to be some change to how we manipulate, for example, this load drop compensation. It's a typical control strategy that the utilities use, where they have a load tap changing transformer that when load is high, they increase the voltage at the substation. When load is low, they drop the voltage at the substation. But that leads to some problems, especially, for example, under these conditions, where I have a lot of solar power in the beginning of my circuit, and the load drop compensation makes my voltage drop even further than it should and goes below the requirements for maintaining power to customers. Okay, so high use of solar even on circuits is a challenge. But it's even more of a challenge if we want to do this for the entire state. This is an example of a week where the entire state demand, okay, is shown here in the blue. Okay? And we introduced additional wind power and wind turbine dynamics. And that's what you see down here. This is the wind power that we could get when we met 33% of the energy delivered to customers is from the solar and wind power that we have installed. And what you can see here are a few challenges. What's one of them? So what's the problem with this? At this point here, I need every single power plant that is already in the system to produce power for me again, but only for a short period of time, okay? Because then I don't need them to produce much, because I have some wind power that came back online. So as we introduce even up to 33% wind power, we can't retire any of our old power plants. We need them all during some points of this particular week. Here's another challenge. During this period of time, okay, right here, typically the base load power plants would want to stay on. But they're not allowed to stay on if we want to accept this wind power, right here. Sometimes we have a contractual obligation to take the power from these systems. So sometimes it's even legally not possible to accept this wind power. So this is going to be curtailed. Okay? We can't use that wind power at that time. Sometimes in the middle of the day, we need to go from having balance plants produce a whole bunch of power to ramping down suddenly if we're going to take this wind power again. And then we have these up and down, hour by hour dynamics that no power plant's going to want to support. And we have ramp rates that are unprecedented. The California ISO cannot dispatch plants fast enough if they're going to meet these kinds of ramp rates. They only tell plants to dispatch every 10 minutes. Okay, that's the finest resolution they have. So it's very important to have something that will complement wind and solar power that can be dynamically dispatched. Finally, these dynamically dispatched power plants actually produce more emissions than the typical power plant does. So what we did is we simulated the dispatch of balanced power generators according to some scenarios where we have high wind and solar penetration. And we assumed that we couldn't import that balanced power. We had to produce it all in the state. And we dispatched current part-loaded in-basin power plants and installed additional power plants if we needed them. Okay? And that gave us spatially and temporally resolved emission fields for the case of high renewable penetration and in-state balanced power generation. And what that did is that suggested to us that we actually, even though we have 33% renewables, and on average have a dramatic reduction in pollutant emissions, by turning those power plants on and off, by ramping them up and down during this week, we actually have worse air quality. On average, way lower emissions, but worse air quality. It's not that much worse, but it's surprisingly worse, where I have 1 microgram per meter cubed additional particulate matter, or about 1 ppb of ozone increase in the place where it matters the most, in the eastern portion of the basin. So dispatching our current inventory of power plants is not a good idea either. So I think a better way to do this is to actually do some things like making hydrogen and then using that hydrogen in fuel cells, kind of like we did in that residence, but at a scale where it makes a lot more sense. Because on a massive scale, where we have to store gigawatt hours of energy, one of the cheapest ways that we could do that is by using compressed gas storage. So this is an example of a simulation we did for Texas. It turned out that's where the study was in this particular case, where we have wind power that is shown in the green, okay, and we have the demand that's shown here in the magenta color, okay. So the net power, okay, goes to either electrolysis, which is shown in the blue here, okay, or to fuel cells for providing the power that the demand requires, okay? So what you can do, you can see here, is that these high wind days end up supporting these low wind days, and you can move wind energy from one day to the next, as an example. And what we did is we looked at an actual salt cavern that was in this same Texas area as the main energy storage equipment that we used. A salt cavern. This is an underground cavern that was mined for salt, okay? And it contains a salt liner that's actually pretty good for gas storage. And we simulated compressed air energy storage and hydrogen energy storage for those same two cases, okay? Using that same wind power, using that same demand, using that same salt cavern for each case. And what we found is that the volumetric energy density of the compressed air energy storage makes it limited. And you can see here, we went between a maximum pressure of 135 bar and 45 bar. And you can see here, the compressed air is sitting at its maximum for the early days when you have too much wind. And it goes all the way to the minimum when you want to use more of that compressed air energy storage. But the hydrogen storage works no problem for that same 1 week of simulation in October. Okay? In addition, you can store and shift power seasonally using hydrogen energy storage. Again, the same volumetric energy storage resource is that cavern, that salt cavern, but you can see the compressed air use in that salt cavern was limited in many days. But over the entire year, you could see that the pressure kept building up, building up, building up in the winter, where I have excess wind, and coming down, shifting most of the wind power to the summer months when electricity demand was higher. This, I think, is going to be one of the most cost-effective ways we can actually complement wind and solar power in the future. And we're studying with Southern California Gas Company not only the use of salt caverns, but the use of the natural gas system that already exists as a means of storing this, as a super low-cost means. It already exists. This is an example of the Southern California Gas Company facilities. But not only do we have these pipelines and everything that you see going on through here, but we also have massive underground storage facilities that are already in operation by Southern California Gas Company. And you probably noticed this one right here, right? Do you guys recognize this location? Yeah, you guys recognize it, right? It's really close by. It's huge, too. It's a massive resource, a massive storage capability for shifting massive amounts of energy. As a matter of fact, it can store up to 11 terawatt hours of electricity using a typical combined cycle power plant to make this natural gas into electricity. 11 terawatt hours. And in our studies, this suggests that we can actually go all the way up to 50% renewable penetration and store everything in just the existing resources. No problem. Okay? I think it's a pretty interesting idea to think about. Okay, the final thing that I'm going to talk about, which I hope will only take a few minutes, is smart grid technology. Because we've been fortunate enough to work with the Southern California Edison company on the Irvine Smart Grid Demonstration project. If you're familiar with the area around UCI, there's the 405 and 73. This is Irvine. There's Newport Beach. This is the UCI campus right here. Okay? And starting from this MacArthur substation right here, that we installed 2 new circuits. One of them is called the Arnold circuit. They're both 12 kV circuits. The other one's called the Renewable circuit, and you can see here. And there's a whole bunch of interesting new features that we installed in these circuits. But notice in particular that they touch each other in a few places. And there's some loops and circles here. That's very unusual in distribution circuit design. And the key idea there is that we want to improve the reliability by enabling power to flow in all sorts of directions. In and out, you could have different resources in different places. We also have 30 smart homes in University Hills here that are outfitted with all kinds of smart technology. Here's an example of some of this. This is the Renewable circuit. That's the Arnold circuit. These are URCIs, Universal Remote Controlled Interrupters. So these are those switches that are at these loop locations and at certain locations along the length of these smart circuits that allow you to switch power on and off in small segments. Okay? Very quickly. Plus, we have energy storage. We have a 2 megawatt battery on the Renewable circuit here. We have all kinds of community energy storage and residential energy storage and smart appliances and electric vehicles at every one of the homes. So we have high penetration of solar power, high penetration of vehicle use, okay, electric vehicle charging, and all of these are being used to study the dynamics of increasing the use of electric power and electric vehicles. We also have, I think, one of the best microgrids for studying the dynamics of increased renewable power together with traditional power generation. This again is the UCI campus. This is the central park around which the main academic units are built. This is the University Research Park, and this is the same set of community. This is the same community here where we have those smart homes for the ISGD project. This is where I'm located. So you can see here our fuel cell vehicles and our energy research center here with the same solar photovoltaic panel there too. Okay, so the ISGD circuits are right here, one going right through the middle of campus, okay, and the other one going around campus here. And the microgrid is centered right around the central park of the campus here, but it gets its electricity primarily from the same Edison MacArthur substation, the same substation where the other smart circuits are coming out of, but then has our own UCI-owned 10, 12 kV circuits that serve the rest of campus. And we have a central plant. At the central plant we have chillers, we have a gas turbine that can produce about 16 MVA, a steam turbine about 6 MVA, run off of natural gas today, okay? We have a thermal energy storage system, the largest thermal energy storage system above ground west of the Mississippi. Arizona State has a bigger one underground. But anyways, we can shift 60,000 ton-hours of electricity. That's a lot of cooling that we can smooth our overall load profile with, okay? Plus we have rooftop solar PV. We have only 1 megawatt that's installed, but we're going to have 5 total after Wendell gets done with everything he's doing. As a matter of fact, we may even already have 2 of that online. I don't know if you know that, Dave. Okay. Plus we have some concentrated PV systems. These are actually managed by our program. We put them in for research purposes. And we have electric vehicles throughout the campus, most of them again associated with our program. And we have a 180 kilogram per day hydrogen fueling station on our campus that we use for our hydrogen fuel cell program. And then we've simulated this, especially using this software from ETAP. And you can see the various buses, 10, 12 kV circuits that are all right here. And this is the simulation of that campus. And notice that our demand looks very flat, okay? It still has dynamics, but it's essentially about 16 megawatts for the entire day. And that's because we can dynamically dispatch the chiller plant and the gas turbine. And we take all the solar we can get. Okay, in this particular case, it only peaked out at about 1 megawatt. But what we'd like to do is make more of our power from solar. And if we wanted to make only 20% of our power from solar, we would have to install 14.6 megawatts of PV fixed and 22 megawatts of concentrated PV. Does that make sense? Doesn't sound right, does it? But you have to think about 2 things. One of them is that you have only sunlight during the day. And the capacity factor, typically in Irvine, especially since we have marine layer, things like you guys have here too, okay, for the whole year, you're going to end up with only a capacity factor of around 20 to 25% on a good day. And then you're going to curtail some of it. Because in these times, I can't turn my gas turbine any lower than what is shown here, okay? If I turn it any lower, it shuts down or it doesn't meet the emissions requirements. So I throw away this amount of solar power for this week. Not good, not good. I would much rather install one of those systems that I talked about earlier and use all of this to make hydrogen and put it in my vehicles. Things like that. Okay. So in summary, I hope that you gathered from what I'm talking about that the dynamics of these energy systems are very important to resolve. And sometimes you need a spatially resolved model, even though I've shown you only very, very simple geometries, to actually get the physics right. Okay? And I showed examples of simple spatial solid oxide fuel cell model in an integrated gasification system, but also everything going down to the utility grid network in which the dynamics of these energy systems is really important. And I really think that we need to consider the use of clean, dispatchable energy systems like electrolyzers and fuel cells for use in our future. I think they're the absolute best technology for complementing the wind and solar power that must be our primary sources in the future. As you can probably tell, this is a mishmash of a whole bunch of research projects funded by many different agencies with many different collaborating faculty and research colleagues, not only at UCI, but all around the world, even from Korea, over on the East Coast and the like. So thank you for your attention.
Questions? Yes.
I was curious when you were showing the temperature dependence and the time dependent trace of
Yes.
the fuel cell.
Yeah.
There's lots of little tiny spikes, and I was wondering what your opinion on what causes those are.
Yeah. So the typical thing that happens is that when you have a power demand increase, is you have an instantaneous response of producing more current. And all of the heat generation is directly proportional to current. But not only that, as you draw more current, the voltage drops so that you have this exponential increase in heat generation. Okay? Now, that should not affect the entire temperature of the system, except that you have some interesting things that might happen to the rest of the system, like, for example, your blower power may increase because you see it getting hotter. When the blower power increases, you have to produce even more power to power that blower. And so you have these compounding things that sometimes lead to some spikes in, like, the temperature distribution. Okay? Thank you. Yes?
Yeah, the reforming of the fuel going into the anode compartment of the fuel cell.
Yes.
I noticed you using an ASU and you could use steam reforming, and those kind of processes
Yes.
are relatively endothermic. Have you considered in your model the use of oxygen transport membranes where the process goes from endothermic to quite exothermic?
Yes, yes. Thank you very much. Yes, we have considered things like that. And of course, there are not only the oxygen transport membranes that can do that, but you could also just do simple partial oxidation, which is exothermic too. But the key thing that we have found in our study of the systems is that typically the endothermic fuel processing systems have more synergies with what the fuel cell is doing, because the fuel cell reactions are always exothermic. They're always making heat. You actually many times have a hard time getting rid of the heat. And so if you can make a system that actually well utilizes that heat and the steam also that it makes naturally, that those kinds of systems have higher efficiencies than the ones that have exothermic fuel processors. Okay? There are many cases in which, though, this exothermic fuel processing might make sense. For example, if you have a really complex fuel. Okay? Complex fuels, it's very difficult to design a catalyst for a broad spectrum distillate fuel, for example. But oxidizing fuel processing techniques can do that more readily.
For example, coal.
Correct, correct. Coal is one of those complex fuels where it makes a lot of sense. I totally agree with you on that. Yeah.
You done any sensitivity analysis on the system in the sense of what moves the needle? I mean, there are so many different things that one can in principle change in order to improve aspects of energy use.
Yes.
But what is the system actually really sensitive to?
Yeah, if you look at some of the publications that I referenced here, you will find that we have done sensitivity analyses on occasion. We don't always do it. Maybe we should do it more often. But yes, and there are certain things that always seem to kind of come up as really important to efficiency, as an example. That's not the only parameter we'd be concerned about. But efficiency often has a really big correlation with fuel utilization, which is kind of obvious. But it also has a big impact on current, okay? And then we've done sensitivity analyses that talk about, okay, what about the cost of these systems? And then you find a lot of things like operating current density as being kind of one of the most sensitive parameters. So for example, if you can go to higher current density cells, the cost just drops really dramatically and things like that. So, and I can't even go over all the parameters that we've actually looked at, but there definitely are certain parameters that almost always jump up at us as being most important to assure can be accomplished well to get an efficient system. But we could do more of those because there are so many parameters that we could investigate. Thank you. Yes?
I was wondering, you were talking about sequestering the CO2, and I was curious at what partial pressures it comes out and at what temperatures.
Yeah.
Because a lot of the challenges is dealing with really low concentrations of CO2.
Yeah. Okay, so be ready to be shocked. It comes out at a partial pressure of 1. You're not shocked? Okay, so no, the key thing is this. Fuel cells are very different and have a very distinct advantage in comparison to almost every other power system that we use today. And that is that we don't mix the fuel and the air. We don't mix the fuel and the air. So what comes out of the anode compartment is a mixture of CO2 and water that if you simply cool, drops all the water out. Okay. That is a remarkable savings when you're designing a power plant for CO2 sequestration. Okay? And it's one of the reasons why that one example I started off with, that it had the CO2 separation but still had 60% efficiency, was able to be achieved. That's one of the reasons. But fundamentally, this is a very different system because I always keep the fuel separate from the air. And as a result, I mean, in almost every power plant, otherwise we have to separate all that oxygen and nitrogen away from the CO2, and it just takes so much energy that we end up having sometimes worse, well, we always have worse efficiency, but we even can have worse emissions and everything because of this. Not as attractive.
If you're driving a fuel cell with natural gas, you're
Yes.
using hydrogen, presumably.
No. If you run a fuel cell with natural gas, okay, what you end up having is only CO2 is produced in, well, CO2 and water are produced in your anode compartment, okay? That is not the case for a proton exchange membrane fuel cell, but we're probably not using those in power plants, big power plants in the future. But for solid oxide and carbonate fuel cell technology, all of the CO2 is made in the anode compartment. It's just CO2 and water at the end. Yes?
One of the strategies you can use after you have formed a sort of a synthesis gas mixture,
Yes.
reforming,
Yes.
you can go through water gas shift,
Yes.
and then separate out the hydrogen through a hydrogen separation membrane.
Correct.
And then you do it at very high pressure, and you can sequester the CO2 prior to the anode compartment.
Yes. Yeah, you can definitely do that. In the one system design that I showed you, we did not do that because we wanted the endothermicity of the reforming reactions to actually occur in the fuel cell to help cool it. Yeah, to help cool it. But we also have looked at similar integrated designs where we take the CO2 out already right away and we put that into sequestration. And we use similar technologies to what you just described. That's a very nice plant design, I think.
I mean, the potential advantage is that you to force the hydrogen through the membrane, you're at high pressure.
Yes.
And it could be at 100 psi or 200 psi.
Yeah.
And it works.
And that's compatible with some of these gasifiers that operate at high pressure. Okay, so you end up having gasification that's well suited to that separation technique. Yeah, that's very nice.
Question for you,
Yeah.
Jack, about storing hydrogen, perhaps right underneath us here, this big cavern,
Yes.
or in the natural gas pipeline. As you know, there's still a lot of nervousness about the San Bruno
Yeah.
explosion, which was, of course, natural gas, not hydrogen. But with hydrogen, isn't there a greater risk of, a safety issue here?
Yeah.
And do you really anticipate that the state regulatory agencies would be comfortable putting hydrogen into the natural gas pipeline?
Yeah, so there are definitely several key questions that have not yet been answered with regard to, I think, the technical feasibility of doing this. In other words, I would not, at this point, recommend it, even though I think it's a good idea to install to inject hydrogen into the natural gas system, I think we still have to investigate natural gas hydrogen mixtures, the effect that they have on the pipelines and equipment, and in particular the welding and joining components of the natural gas system. But in addition to that, what kinds of concentrations should we allow that would be safe? Okay, and then there's another whole set of questions associated with leakage. Okay, so it's not only the embrittlement and the pipelines and what's going to happen to the infrastructure, but it's also leakage, because hydrogen can leak out much easier than methane, for example. So some of those questions are partially answered. There's been some great research at Sandia National Labs. We've been working with University of Illinois in Urbana-Champaign, and they have some really good hydrogen embrittlement people that are answering some of these questions as we speak. Today, though, we can already store, according to regulation, 0.1% hydrogen. 0.1%. That's permitted. It's not much. It's not much as a percentage, but it's a heck of a lot of energy storage already. So with SoCalGas, we're looking at, with SoCalGas, we're looking at, okay, let's see how much that is. And let's try putting it in and then seeing if that makes any difference. Okay, so it's pretty interesting. I think that will evolve over time. I eventually think, and I think I told you this in your office earlier today, that the whole natural gas system, when we run out of natural gas, is going to be used as a means of delivering renewable gas. Okay? It might be renewable produced methane. Okay? It could be that it's synthetic natural gas, but it could also even be hydrogen when we figure out if we can do it. So, yes?
In terms of leakage, what about hydrogen and salt mines? What kind of
Oh, as a matter of fact, okay, so the salt caverns, which are usually hydraulic mined, so they basically inject water underground. They take the water back up. Of course, the salts are water soluble. What ends up happening is you end up forming this shell around the entire mining cavern, okay, the mine cavern, that is primarily a layer of salt that's pretty impenetrable. And as a matter of fact, Praxair is currently using a big salt mine in Texas to store hydrogen at the same sorts of pressures that I just showed on the chart here. And they're doing so very successfully without a lot of leakage. I don't know all the physics behind how that works. Perhaps you can inform us on that. But apparently, it works quite nicely.
I wonder if you know that we're sitting on a natural gas bubble.
You do now.
Absolutely 100%.
That's the leakage that was actually.
It's as large as itself.
Yeah.
Right underneath.
Yes. I thought you'd like that part. Yes.
Yeah, have you considered using that electrolytic energy to convert carbon, since we are all concerned about greenhouse gases? Using that electrolytic energy to convert carbon dioxide to carbon monoxide, and then reacting that with hydrogen to form synthesis gas.
Yeah.
And then going to something very corny like FT chemistry to make liquids.
Yeah, we can do Fischer-Tropsch, we can do that. Yeah, those are all good ideas from my perspective. Co-electrolysis, CO2 conversion to CO subsequent reaction with hydrogen. Yeah, those are all really nice ideas that fit into this overall framework very well. I just talked about hydrogen. It would be very complicated to get into all those possibilities. But that's very nice.
From a storage aspect,
Yeah,
this whole infrastructure.
yeah. Already, yeah. Yeah, it's very nice.
Well, let's thank Jack